Come on. Okay. So if we look at a second order inhomogeneous linear ODE. So we have y double prime plus py prime plus qy plus nothing equals some function, non-zero function, g of t. And then same old initial conditions. Okay. Now, we have a way of solving this. We kind of have a solution formula, but what I want to do with that is show from that solution formula that we have, which is very different from what is taught in typical intro ODE class about how to solve this problem. Now I'm going to connect the two. So how can you solve this? So the way that we have, based on everything I've covered here, is you rewrite the second order ODE as a first order system. And so what we have is, okay, so the vector u of t, actually, no, I don't need that. So y of t is equal to the first component of this expression is a e to the at times vector of initial values plus the integral of e to the a times t minus s times the source term of our linear system, which is a function, the vector has 0 as the first entry, and then g of t, this function g of t is the second entry, ds, okay. Where, in this case, the matrix A is the matrix we've been dealing with, 0, 1, minus q, minus p. So in previous classes, I've shown I've worked out 2 of the cases in here, and the other one I left to homework, how you get e to the at, the matrix exponential, and then we always have a vector of initial values here. We always have a source term here. You work all this out. You take the first component, and that's your y of t. All right, so that's what I've shown you. But how is this done in classes? Well, there are 2 techniques that are typically taught in a intro ODE class. I'm curious as to whether any of you might remember either method's name. Okay, solving this kind of ODE where you have something here, so it's not 0. Because in a class like that, you learn how to solve this when it's equal to 0, and that's where you do the characteristic equation, you take the roots, and you have those cases of like, oh, distinct real roots and exponentials, and complex roots, sine and cosine. And then they throw this in here, and they teach you 2 methods in particular for solving it in that case. That's for a different ODE.
Never mind.
Okay. Well, the names they might ring a bell. What is the method of?
Undetermined?
Yeah. Yes.
Okay.
Yes.
I don't know why I have to hear method of, but.
Okay, whatever works. Undetermined coefficients. Okay. And what about the other one?
I don't know.
Okay. Variation of parameters.
There we go.
Okay.
I would have gotten it with variation.
Oh, okay. Funny when you mentioned method of. One time I was in a conference. I was actually in Bulgaria, and I'm giving my talk in a session with a handful of other people. And this professor, who he was clearly American, but he was actually a professor at somewhere in the Middle East, like Dubai or something. So he's an expat. And he says, there's a common theme for all of these talks. They're all about some kind of method. And it's like, is he joking? Is he being sarcastic or something? But I don't think he was. It's like, okay, that's illuminating. But yeah.
But you said like that's a very American way to.
Oh no, that's just incidental. But the fact that that's a pretty flimsy common theme to. I mean,
Yeah.
It's like, oh, almost some kind of method. It's like, yeah, this literally is what this conference is about.
Oh wow.
Yeah, it's like, okay, that's, I don't know. So probably, I guess because a lot of us talk about method in the title, including line. Yeah, it's like, I don't know. It seems like a weird thing to say. Never mind. Okay, so what my plan for today is to show how you can take this solution formula and obtain a solution formula from this method. So basically, I'm going to derive, because in these ODE classes, well, they might do some work to show where a method comes from, but then the students just learn the solution formula and off they run with it. But I feel like those kind of derivations, whatever they tend to do, are really just partially complete. But here the idea is to build up everything. So that's what I'll do. I'm going to use this as my starting point and get to what variation of parameters would give. Okay. Yeah, actually, I think what they do is they make an assumption about what the solution looks like. It's like, well, how do you know about the solution that assumption is valid? Okay. Do I have my phone here? Oh. I need
to just take a picture.
Well, I'd like to. I'll have it with me anyway. Yeah, still no one in that room. Decide not to be or something? Okay. Okay. Now, actually, this formula I want to keep. I'm going to work with it. So the way I can do this is using a form of a matrix exponential that I arrived at last time. So everyone from Tuesday is meant to set this up. Okay. Now, the thing I have to recall, the solution of the homogeneous version of this problem is the similar idea, first component of e to the at times your initial values. Okay. Now, and the other thing you need to recall, this is just from Tuesday, is e to the at can be written as this matrix product, x of t times x of 0 inverse, where x of t consists of has its columns solutions of our first order system. So xi of t prime is equal to a times xi of t. So you're using homogeneous solutions, and that defines your matrix exponential. Okay. Now, so I need to remind you of a relationship between this first order system of ODEs that I've been dealing with and the original second order scalar ODE. Because xi of t has as components, I'll call them yi of t, yi prime of t. And this is a solution of the original second order ODE. Okay. Because this is equivalent to this first order system where the first component is always y in here, and the second component is always y prime. Because that's how we rewrite higher order ODEs as first order systems. The first component is always a solution of a higher order ODE. The other components are always that solution's lower order derivatives. So here we're dealing with the first order system, but now we need to tie it back to the original higher order ODE. Okay. So what I want to do is, because of a problem with this solution formula, is it's not easy to see how this solution relates to solutions of a homogeneous problem. It's not expressed in that way. Because so the way it's typically taught for solving these kind of higher ODEs is, okay, get solutions of a homogeneous version. Now we work with those to get solutions to the inhomogeneous version. But we don't have any of that here. So by writing the matrix exponential this way, now I can do that. Now so I'm actually going to substitute this in here. But before I do that, I want to rewrite this part a little bit. I have e to the at and the integrals with respect to s. So I'm going to pull the e to the at out. Okay.
Question. That is e at the beginning. You got like the e1 transpose, right? But then the e to the at, that is times that vector, correct?
Yeah, matrix vector product.
Matrix vector product. Okay, I was just making sure because I think they're. I'm misplacing some of the parentheses and stuff.
Oh, okay.
Yeah, I got it now.
Okay.
Okay.
Okay. Now, the thing to keep in mind is e to the minus as. That is the same as e to the as inverse. Because if you take e to the as times e to the minus as, the exponents will add together or cancel out, and you'll get e to the 0, which is identity. So I'm going to use that because I could use this with t replaced by minus s, but it's going to be better to work with the inverse. Okay, so now I'll start substituting. Wherever I see the matrix exponential, I'll put this in its place. So I have x of t, x of 0 inverse, y naught, z naught, plus, okay, the same thing again here. Okay, and then integral from 0 to t. So now I need to take the inverse of this and put it in there with s instead of t. Now remember, the inverse of a product is the product of the inverses in reverse order. So when I put a of s, e to the as inverse in here, I first take the inverse of this, but that's just going to be x of 0. And then I'll have the inverse of this going next, so that's x of s inverse. And then I have this vector here. G of, oh, that should be s, whoops. G of s. Yes. Okay. Now, so one nice, actually there is something here from what I've written that can now be simplified.
Oh, I think this. Is it something to do with the limit of integration stuff?
No.
No, okay. I guess you got 2x tx 0 inverse. Like you have 2 of them, you could pull out. Oh no, that's multiply times the integral.
Okay.
I don't know.
All right. Now keep in mind, anything that does not depend on s, you're allowed to pull out of the integral.
Oh, okay. So you can pull out the x of 0.
Yeah. So, yeah, this I can factor out. But once I pull it out, then what happens? Anyone?
Does it simplify with the inverse that's there?
Yeah. x of 0 inverse times x of 0 identity.
Okay.
So these will cancel. Yeah. Okay. Now, another thing we do is everything is big mess in square brackets. At the end, that's a vector of 2 components. But we only want the first component, because that's our solution y of t. So where we see x of t here, we really only need the first row of it. Now, I've shown you this is what x of t looks like, but each one of these columns, oh, that should be a vector one. As a first element, yi of t, or y1 of t, y2 of t, those are homogeneous solutions. So now I can introduce those. So what we have is E1 transpose x of t is a vector, a row vector, consisting of y1 of t, y2 of t. So this is a big part of the goal, is to introduce homogeneous solutions into the formula, because that's what these techniques taught in these classes work with. So I have y1 of t, y2 of t, and then the rest of this, x of 0 inverse, y naught, z naught, okay? And I could do that over here too. y1 of t, y2 of t, and then this integral, x of s inverse, 0 g of s. Oh, actually, yeah, okay, yeah, that's right. Okay. Now, this is a column vector. And this whole integral, also a column vector. So once those column vectors are obtained, then we take the dot product with vector y1 t, y2 of t, and then we have our solution. But what this vector here and here shows is that the solution is a linear combination of y1 of t and y2 of t. Okay. It's just that this is a constant vector. This is a vector that's a function of t. Okay. So when I say linear combination of y1 and y2, the coefficients, or I should say the parameters of that linear combination are varying with t. They are functions of t. That is the basis for the name of this method, variation of parameters.
Okay, constant vector, and then the other one.
Yeah, but this column vector has components that are functions of t.
Yeah, okay.
Yeah. So it's a linear combination of y1 and y2 with varying parameters.
Okay.
Yeah. Okay. So now the next thing to do okay. Is work this out. We have x of s inverse. So for that, we could use x of s is a 2 by 2 matrix where each entry is a function. So now we can use a formula for the inverse of a 2 by 2 and work that out. So we keep in mind that x of s is equal to y1 of s, y2 of s, y1 prime of s in the second row, and then y2 prime of s. Then the inverse would be 1 over the determinant. So that'd be y1, y2 prime minus y2 y1 prime. Okay. And then the rest of the formula, so you swap the off-diagonal entries, swap the diagonal entries to, and then negate the off-diagonal entries. Okay. Okay. So then what I want to do is take that inverse, it's multiplied by this vector, that has 0 for first component and g for the second component. So now when you're multiplying by a vector like that, when you multiply a matrix by a vector, you're taking a linear combination of the columns. Well, the first component is 0, so we don't need the first column of the inverse. We'll just multiply g by the second column. So that's going to turn out to be 1 over this determinant. And I'm going to be lazy here and drop the of s. Everything in here is a function of s. Okay.
Had to do that earlier.
I
was tired of writing it.
Yeah, so then I have minus y2 g, and then y1 g. And all this is a function of s, so I put one big old of s there. Okay. Okay. Now, this expression in denominator, y1, y2 prime minus y2, y1 prime, that expression comes up often in intro ODE classes. It has a name. Does anyone happen to call what that name is? And it is a determinant, but in an ODE setting, it has a, I guess like a, I don't know if it's named after a person or something, but it starts with a W. Wronskian. Yeah. So that right here, that determinant is often written just a W of y1 and y2. It is the Wronskian. And the key here is that you need to have two solutions such that the Wronskian is non-zero. That is what confirms that the solutions are linearly independent. Otherwise, x of s inverse would not exist. Okay, well, it doesn't put a lot on this board. Questions about any of it? Okay. So what I need to do now is I need to take these this vector, the entries of this column vector, and incorporate that into here. And that means actually carrying out the inner product of with this vector, row vector of y1 of t, y2 of t. Well, we're not going to actually carry out the integral. We'll still leave it as an integral.
Oh, okay.
Because these functions can be anything.
Yeah,
yeah.
That's true.
That's okay. That's still how you describe the method of variation parameters, that there are a couple of integrals to work out. Okay. All right, now, as a notational convenience, I'm going to let this vector, x of 0 inverse times the initial values. That's a column vector, so I'm going to call it C1 and C2. Okay. So now I can go back to the y of t I had before and write it this way. Y of t is equal to, well, okay, I'll do an intermediate step. That's closer to what I had. Y1 of t, y2 of t, and then the next thing was this vector, okay, plus y1 of t, y2 of t, integral, and now what I have is this column vector, which is, well, I've 1 over Vronsky. I'll just write it that way as a function of s. And then the column vector I was arrived at from using the inverse was minus y2 times g, and then y1 times g. Okay. So now I want to eliminate all traces of linear algebra from this, and write it out like it would appear in an ODE class. So you get C1 y1 of t plus C2 y2 of t. And this is often labeled as like YH of t, which is the homogeneous solution. So if you think of C1 and C2 as arbitrary constants determined by the initial conditions, this is the general solution of a homogeneous equation where g of t is 0. So that's that part. Plus y1 of t, u of t, plus u1 of t, plus y2 of t, u2 of t, where u1 is the first component of this column vector. So it's minus y2 times g over Vronsky. Okay. And then u2 of t is second component. So it's y1 times g over Vronsky. My arm is tired. This is good I don't have to write it on the board in the next class. Okay. Oh, whoops, it's still a little more right. This part is known in PDE classes or ODE classes. It's like often written as abbreviated as YP of t. That's called the particular solution of a non-homogeneous ODE. So every solution to the non-homogeneous ODE has this form. You have some particular solution, and then you add on any solution to the homogeneous problem. You need that because it has to be able to satisfy whatever initial conditions you have. So everything I've just written here, or at least this last line, is exactly a method of variation of parameters. And exactly how you would see it written in ODE text. So now you have the full story of where the formulas come from. trying to remember like how it's normally derived in those kind of books, but and you end up having a system of 2 by 2 equations to solve, which is how this part comes about. But you are doing some kind of matrix inversion. Just not remembering the details, but okay. So, questions about any of this? Or homework stuff? Well, turns out we only have 5 minutes left, so that actually worked out pretty well. Yeah, I think what happens is, okay. I'm just going to try something over here and on this other board. And see if it leads to where I think it will. I think what's done is you assume that the solution has this form, where y1 and y2, okay, so you assume your particular solution is a linear combination of y1 and y2, where u1 and u2 are unknown, and they're functions of t. And that's not a product as much. So you substitute that into the original ODE. So yp double prime plus p yp prime plus qyp. This p and this p are not the same. Not the same.
I remember all this, or I remember doing a problem in your class you cannot figure out stuff.
Yeah. Remember what?
I just remember it was like the one big, like in 610, it was like the hardest or the longest time I spent on a problem, and it involved this at some point, but
Really?
a lot of other things too. I'd have to pull it back up, but.
Yeah, I remember what the problem was. Oh, okay.
Yeah.
Because then if I substitute this in here, got to use a product rule and all that. So we have something like y1 double prime u1 plus 2y1 prime u1 prime plus y1 u1 double prime, and then the same thing for y2 and u2. Oh, that's going to get really lengthy. Okay, plus coefficient p times first derivative. This is why I wasn't tired enough already. And then plus q times but then the parts that involve just plain u1, you gather all those together, and you end up with like y1 double prime plus py1 prime plus qy1. That's a homogeneous solution, so those terms all go away. So thankfully, a lot of terms can be crossed off. Okay.
A lot of them cancel out once you factor out a u.
Yeah, so then you have, okay, all of this is supposed to equal g of t. But then for the rest of it, I think it's some sort of assumption that about certain things being 0, but okay. And because U1 prime is just going to end up being, you know, the integrand. And if I multiply the integrand by y1 and I multiply this integrand by y2 and add them together, you get 0. So apparently this plus this is 0. But I don't recall like the justification for that assumption. So like these terms also go away. Yeah, that's, and then y1 prime, y2. Yes. Yeah, that part I don't know about, but yeah, unfortunately I forget what happens here, and I'm out of time anyway. So that's been driving me nuts. I'll look back at my old notes and see, or I might just stay here till 5:60 and work it out. So, okay, but you all are off a hook, well, for a half hour. Okay, so probably do something with undetermined coefficients next time. So, okay, so until then, stopping recording now.